Professor Naira Kovakimian from UIUC. I'm also personally excited that she's here, since we do things in the lab that we use several of her tools, the tools that's used in the lab. But most importantly, I'm excited because, for me at least, Naira, she impersonates or personifies, what it means to be a wholesome faculty. Okay, to be like outstanding on research, to have industrial impact, and you have your own companies, as we try to do, for example, with Andrew here, but also, have impact on people, right, through the research, like elderly care, as Naira has done, but also, to the students and other like young professions, right? Like, for example, Naira has received multiple awards, not only for the research excellence from CCS, from Society of Women's Engineering, and many, many others. Naira insisted that I will not enumerate all the awards, but also she has received multiple awards from the same professional and teaching association, including, again, CCS, on her teaching and the quality of the mentorship. So it's a pleasure having you here. So thanks so much. And yes, without further ado, please take it from here.
Thank you for the invitation. Thank you for hosting me. Thank you for the nice introduction, and welcome to this last hour talk of the Friday, right? So hopefully everyone is looking forward to the weekend. The presentation will be more entertaining than on technical depth, so everyone can enjoy the time. I came to United States back in 1998 when I was invited to Georgia Tech. The group was working on stability and flight control design for huge, large-scale, major, super powerful certified vehicles. And as I worked 25 years in this country, the industry seemed to acquire a new face. Today, aerospace industry talks a lot of drones, parcel delivery, agricultural management, emergency response. There are lots of small-scale autonomous vehicles, quite often human-centered, that take a major bandwidth from the industry to support these developments. This transition of industry happened due to the data explosion. CPUs and GPUs became cheap and available. It boosted the performance of machine learning algorithms. Computer scientists started solving some of the problems that we have been trying to solve for years and coming up with empirical performance that was outstanding. From the perspective of aerospace industry, what we see happening, we see that we went from the high altitude to the low altitude space. In the high altitude for the commercial aviation, by enforcing zero tolerance to accidents, public trust has been achieved with 4.5 billion passengers flying airplanes per year. For low altitude space, we don't have such powerful claims. The low altitude space remains highly vulnerable to different uncertainties, with the DCA port collision of a year ago just being a classical evidence when a kind of military training could collide with a piloted passenger jet. This means that at a low altitude, we have lots of problems to solve. So a few years ago, I was at Georgia Tech for a seminar visit like this on a cold January in 2018, when one of their professors, Evangelos Theodorou, who was one of the finalists for this Alpha Pilot competition, which was created by Lockheed Martin and MIT to challenge drone racing environments, asked me a question if we could bring the L1 adaptive controller to this environment, because he was trying to compete. And the minute I thought about it, the first thing that struck my eye is that there is no flight envelope here. If for the large airplanes for which we had demonstrated the performance of our L1 adaptive controller in real flight, which included subscale Boeing 757, Learjet, F-16, coming to this environment, I realized we won't have the flight envelope. The flight envelope that you see in front of your eyes when you're flying transatlantic, or even from here to Indianapolis that I flew. So this flight envelope disappears. So we have vision-based sensors that are mapping the environment every millisecond, creating the new path, updating the new path. So we need type of control algorithms that would be suitable to work with these environments. So let's move forward and see what does it mean to have an autonomy pipeline. The autonomy pipeline has this type of sensors, which are mostly vision-based sensors, mapping the environment, helping the planner to generate a trajectory, which the autopilot has to follow. So in this process, there are fundamental questions coming up. So what if the autopilot cannot deliver what the planner is asking to do? And what if the planner does not account for the errors in the environmental map? So the autopilot needs to have awareness of its limits and be able to communicate it to the planner to generate trajectories that it can safely fly along. And the number one question that we face here when we talk of this communication is the language barrier. Because these vision-based sensors that are processing the visual information, imagine like self-driving cars, if some of you have autopilots with Tesla cars. So the pedestrians or the traffic of the daily commute cannot be modeled deterministically. The right representation of these are the stochastic models. And naturally, these vision-based sensors that map the environment, they give inputs that have stochastic origin. The autopilot, on the other hand, can be a PID controller. So how should they communicate and how should they work together? Like an ontology challenge. I have a student who works at Waymo who tells me that the motion planning group has 500 engineers, the control group 4 engineers, and they both do their own optimization and they put everything in some simulations to test and validate. The question that we asked is how to make sure that there can be proofs and rigorous guarantees when these methods and frameworks are born in different worlds and have different formulations. How can we get, for example, distributional robustness guarantees for deterministic L1 adaptive controllers that we have flown so that the autopilot can make use of these bounds? So these types of questions are important to certify an autonomy pipeline. So let's look what guarantees we can expect from machine learned models. The trained model will produce us an estimate of the dynamics within the model class that we choose to model, for example, say a neural network. It will be trained on some data, which is an empirical distribution available from past trials, from failed crashes. So there is some empirical data available that the machine learning model will give us a learned model certificate, which we refer like model risk. It minimizes an expectation of a loss function over training distribution. And these guarantees are distribution-dependent performance guarantees. They can be extended to Wasserstein ambiguity sets around empirical distributions. Shifts, robustness to distribution shifts. When you go and implement this machine learned controller or with a machine learned model in the real world, you'll face distribution shifts, the causes of which can be either insufficient data, to which the machine learning community refers like epistemic uncertainties, they are learnable, or inherent randomness, like the disturbances that you can't predict on any day, what would be the disturbance on a transatlantic flight. These are unlearnable uncertainties. Engineers in industry like to call them known unknowns, unknown unknowns. So on one hand, we have class of robots for which it's an acceptable cost to crash infinite time to collect the data, to improve the learning, to do data randomization, pick and place robots, exoskeletons that you see here. It's an acceptable cost to increase your database, to improve the learning. But it will be prohibitive cost to assume that you can crash infinite number of airplanes or missions to Mars to collect data, to train, to improve your model, to improve the learning. It's kind of becoming a chicken egg problem if you look at it from the machine learning perspective, which you can do in the first case. You can't do it with safety critical systems. This is where we need architectures that would guarantee safety and predictability in its application and enable safe use of learning algorithms. So these architectures that we aim to establish must be able to use distributionally defined guarantees in a rigorous way. And they must be independently verified by some Monte Carlo methods to help us to merge the design space with the test space. And the reason I say this, because, for example, the way FAA certifies flight controllers is that they get these gain and phase margins across the flight envelope through gain scheduling, concatenation of linear baseline controllers, and they test it all in Monte Carlo environment with some uncertainty distributions. And if it all checks green, it's good to be certified. But it would be good to have theoretical guarantees that you would know how to get distributional robustness guarantees for deterministic controllers and to merge the design space with the test space. And we want the safety to be decoupled from learning, because quite often you can not afford to have a luxury of large data sets. You may have poor training. You may data disappearing from your imaging sensors due to occlusions or other kind of disturbances. So you want to have safety guaranteed independent of the learning, and the learning to give you the opportunity for improving the performance intermittently. So whenever certain thresholds are met, kind of the learning can be used to improve the performance. So this brings us to this field of distributionally robust control, which is a relatively mature and established field. In some sense, we are newcomers to this distributionally robust control field. The fundamental difference that we are emphasizing in our research is that we are not designing distributionally robust controllers. We are trying to establish distributional robustness bounds for our deterministic controller. This means that, for example, at any point, we are not running zillion samples and picking one. We have flown a deterministic L1 adaptive controller for which we had gain margins and time delay margins. Now we're trying to establish how robust it will be in terms of distributional robustness bounds, in terms of data shifts. If we can establish those bounds, then these bounds can be used by the planners. That's our difference. So what we do, say you have a machine learned controller, which is denoted here by pi star. When you deploy it on a real system, you will face distribution shift. And here is where we bring in the L1 adaptive controller to robustify and to maintain it within a tube around the nominal distribution. L1 adaptive control is not new. I have presented here in Michigan twice already over the past 20 years. It was established by our group back in 2005-06. It's a simple filtering mechanism to decouple the estimation loop from the control loop to enable fast estimation rates without losing robustness. Its input-output performance is equivalent to internal model controllers, with the only difference that here we do not have model inversion, while in internal model control loop you may have model inversion. And through this predictor structure, which is a straight feed-forward dynamics, we are able to accommodate saturations, delays, and other type of nuisances from the system as we learn them on the go, avoiding the model inversion. So it has been commercialized, it has been published, and the performance bounds can be represented through decoupling structure. One of the terms is inverse proportional to the rate of adaptation. The other is proportional to the filter bandwidth. This decoupling helps us to tune it differently. One is based on the CPU, the estimation bound, and the other is based on control channel bandwidth. The proofs are done through Lyapunov and small gain theory, well-established tools historically. Here is a brief history of it. As I said, we started in 2005-06. We flew NASA subscale Boeing 757 in 2007-10. Then we got lots of papers with different companies. Raymer commercialized it for evolution autopilots. Caterpillar commercialized it for hydraulic pumps. We got on the experimental rig of Statoil before the oil prices crashed for drilling pressure regulation applications. We worked with Eurocopter, Seagate, and lots of other companies. So in 2015-18, we got the opportunity to test it on manned aircraft. That brought us to this area of safe learning and control, starting this COVID year. Finally, last year, Lockheed Martin flew it on X-62A Vista platform and claimed TRL-6 under ONR SAFE program. So I want to do this brief recap of this Boeing 757 flight test from NASA. This is 5.5% model that NASA built over five years. So 24 groups were funded to fly the controller. Everyone was given one flight condition, 4-degree angle of attack, 80 knot airspeed flight condition, and we had to test controllers for robustness. So I can just run it. This is the stall indicator here. You will see they will push to stall, it will turn red, and they will repeat it.
Try ramping up to 15, okay? Moment around 18, okay? Well, back to normal flight. You ready? Yeah, okay. All right, turn down. Okay. Fuel state is 4.7. Let's repeat that. Climb maintain 1,200.
And they repeat to check the transients because our big claim was the transient performance guarantees.
Repeat that. Slow down a little bit. I'm going here. Okay. Go. Okay, let's stop research. Recover.
They ran out of gas. This is the red indicator. So the reason they repeat because they wanted to test for the transients, which was our biggest claim. Out of 24 groups, 9 groups were invited for flight testing. The rest of the groups were disqualified on the simulation level. So they eventually used the controller to go to the edge of the flight envelope to 28 degrees to do Schroeder sweeps to collect more data for updating the aerodynamic models. This is what you see. The plane was stalling at 12:15, as you saw. Now they went to 28 and they are doing the Schroeder sweeps for updating the aerodynamic models. With that, we reached 2015 when one of my former students called me from test pilot school at Edwards Air Force Base, suggesting me to go and test it on a Learjet model of CASPAN, which is a variable stability system. So it can shut down if something goes unsafe. Here, they didn't have the opportunity to go into stall. The vehicle was not suitable for that, but they could do, for example, landing that NASA couldn't do on the 5.5% model. They had safety pilot for landing there. But here they could go into landing. Let's look their flight test. There was some media here, Aviation Week, like to write about the test pilot school flight test. This was the F-16, which we cannot show. But this is that flight test where they had this accident data from 1967. They could load on this test aircraft of Learjet, make it behave like this accident, where you see the aircraft is released and it gets into roll oscillations and eventually crashes. The pilot luckily survived in this case. This data could be loaded on test aircraft and to test it for pilot's performance. The pilots get licensed by flying this airplane. The first episode is very short because it behaves very unstable. It shuts down, but you will see my student sitting on the left. Students love to go and test their controllers.
Can you get the airplane? You get the airplane?
Now they put the L1 controller and try it again.
Hey, task in 3, 2, 1. Now? So you can feel there in high frequency, I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less. That's good. There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good at pitch. All right, and I have the different complete.
You heard pilot saying there is still something there. I will explain it with stochastic analysis. The deterministic analysis never gave the answer for this something. That's a small buzz, and now you will hear them.
On in ready, tackle. Running.
Engine on.
Okay, power's coming back. My hands are free. 3, 2, 1. Now. Controls fixed.
And
recover, please. Okay, and recovering. Power's back.
And now the pilot corrects it up to 12 degrees. You see the band.
I'm ready to try this now with with a pilot correcting for it. So
Okay, and I'll give it about 1 second reaction time. I am on conditions.
all right, and then recording on my call. Ready, tack.
On. Okay, power will be left throttle. Okay, in 3, 2, 1. Now, one potato and recovery.
And recording off.
And recording off, matching throttles.
So the pilot was able to get to 12, from 20 to 12. Now they go with L1, they get to 3.
And I'm ready for the recording on. Ready,
On. Okay, left throttle coming back in 3, 2, 1. Now. I'm not touching the controls. Nice demonstration. Yeah, check that out. About 3 degrees of left bank. Speeding in the rudder to match. I can feel that.
It is dissenting lipids. Yeah, the setting a bit, but that would be easy to compensate for. Yeah. Okay. I think you got some good data there.
All right, recording up.
Magic power recordings coming off.
So 3 degrees, something left, right? So the deterministic analysis does not give these answers. But when we went to stochastic, we found the answer. So right here also the Air Force Defense Technology wrote about us. I was not aware of it. In the other case, Aviation Week was coming to test pilot school interviewing us. But this one I got from the college. So interestingly, we were on the front page. And this is what Lockheed Martin did last year under the SKUNK program, SKUNK Works of Lockheed Martin. They are our partner on NASA ULI project for technology transition. They flew on this modernized Vista platform with L1. It's their design. And as you'll see here, they maintain quite well in this green with failed right flap. This is only 12 seconds video I got from their social media. They share nothing. So it now goes through future transition, technology transition opportunities at Lockheed Martin. We look forward to more kind of opportunities to work with them. They claim TRL 6 and with the future platform, they are hoping to get TRL 8, 9. And it has to do with the size of the platform, this TRL grows. Some other applications along the way. I like to show this one because this was something that New York Times came and got us into New York Times. That's why it's worth sharing. It's elderly care project. This is the inspiration. This helps to tell why is control important to people outside control, right? You show these cartoons, everyone understands that this is a control challenge. Now they can't lift it, they call friends. And they call friends and communication, cooperation, collaboration. So, and then human safety perception. So this project motivated us, this vision motivated us to work with a psychology professor that was using VR to test humans' perception of safety, which is different from engineering safety. Right? Engineering safety is about lack of collision. Human safety perception is a lot. Why can't I move? Oh, okay. So we come now to this environment. And in this environment, like we said, you have to bring drones to find humans, to save humans, and we have to kind of be able to work with autonomy. So this was brought to me in 2018 at Georgia Tech, and it immediately opened up this. So if we have designed L1 with this historical understanding of robustness, transient, steady state, what we teach in junior level control class, and we address these issues rigorously, and we flew the Learjet. As the world around us changes, new forms of guarantees are needed. So now our sensors are data-driven. We have to talk of distributional guarantees and all these things. So the Georgia Tech colleague was one of the finalists, and he was implementing the model predictive path integral controller on the drones. This is 2020 IROS. This was the year COVID hit. I have to give lots of credits to Georgia Tech students who were going to lab with masks, interns. There was no more than one person allowed to go and do some experiments to integrate L1 adaptive controller with model predictive path integral controller. So the model predictive path integral controller is an MPC solution with learning. It computes optimal control solutions forward in time, updates the control sequence iteratively by sampling thousands of trajectories. This is what we don't like. L1 robustifies their solutions against discrepancies. It can leverage parallel sampling for modern GPUs, handle complex dynamics and cost functions. So they got this IROS paper. This was empirical demonstration that we could bring L1 and integrate with MPPI to clean some of the gates where they were crashing here. They were not the winners. The winner was Scaramuza's team, but they were one of the finalists and they had data, they had experience, and we could test it already after their competition was over. And as you see, we went and cleaned all these gates, showing empirical evidence and getting out an IROS paper. After IROS, we did this MBRL paper. We did some empirical trials. So we augmented a model-based reinforcement learning controller with L1. So the challenge is that reinforcement learning algorithms learn models that are highly nonlinear, and the parameters of these models never match the true parameters of the system because they take some neural networks and train. So they are not kind of ready for classical control type of augmentation. If you want to do it, you have to FNize the model structure. It comes at the price of sacrificing the performance. So we wanted to do an add-on L1 to improve an MBRL performance. So don't touch the legacy architecture, don't touch the assumption, take that high-level MBRL like a black box and see how you can augment it with L1. It was lots of effort. 2 years we were submitting it to some machine learning conferences. Eventually we got it in ICLR in 2024. And we tried it on 5 different models of Mujoko environment, inverted pendulum, swimmer, hopper, walker, and half cheetah. And we got improvement almost in all the cases except for one. Because now we have probabilistic guarantees. Maybe we didn't tune enough because we wanted a single L1 controller to work across all the environments, all the systems without any redesign or retuning, which is our main claim with L1 adaptive controller, that it's easy to design and it doesn't need retuning or redesign. So in one case, we didn't see the improvement, but now we're augmenting an MBRL controller. Things are stochastic, guarantees are probabilistic. So this motivated us to look into this distributionally robust adaptive controller more rigorously. In a recent SciTech conference, we showed augmentation of imitation learning. Where do you need imitation learning? So you have a pilot who learns to fly on simulator, then goes to fly the real system. Here you have uncertainties between the real system and the simulator, which the L1 adaptive controller can compensate for. But if you want to take out the pilot and put an AI agent, then maybe using L1 and justifying is not honest enough. So you want to have some imitation learning that can imitate the pilot. You can collect pilot data, imitate the pilot. So it's the right use of maybe imitation learning policy in this context. But then you want to combine these different robustness characteristics coming from L1 for modeling uncertainty, coming from imitation learning for policy changes, because imitation learning at that point assumes that there is no change in the dynamics. It just replaces the pilot, assuming the dynamics doesn't change, but in reality it changes. So with a layered architecture, you can kind of compensate for both. This decomposition is critically important. And here we show some simulation. This is a toy problem. The NASA model is still being worked out with all its full simulator environment. But with the toy problem, we just showed how bringing L1 on the top of imitation learning can compensate for some of the uncertainties that the imitation learning could not. Now let's do a little bit math. We're half hour through the time, so this will be minimal. So let's put some rigor into all this, right? We're talking so much about certification. So what do? We say we have a deterministic controller designed for Euler-Lagrange equations, which are deterministic. But I go and implement it on the real-world system. The real-world system appears to be highly uncertain, highly stochastic. So we look into nonlinear Ito processes with uncertain drift and diffusion terms. And we understand that these uncertain drift and diffusion terms can both be decomposed into known and unknown components. And we have also aleatoric uncertainty, the Brownian motion that's multiplying the diffusion term. With this, I have to set up a known system, right? Because anytime we want to do analysis of a nonlinear system, unknown system, we need to have some nominal model that we like. We have to set it up in a way against which we do the analysis. So the nominal model, we take the known components of drift and diffusion, but it needs to have its own Brownian motion. The key challenge here is to assume that this Brownian motion of the nominal system and the Brownian motion of the true system, the aleatoric uncertainty component, are completely independent. It's very easy to make them dependent and go through proofs in a second. The challenge is to deal with this assumption when these Brownian motions are uncertain. But this is the honest way of approaching the problem. It took us 4 years to get over some of these assumptions to make the theory go through. So we want to tackle the distribution shift. If I look into the nominal system, I need also some assumptions about the underlying deterministic dynamics. So I get rid of this diffusion term by setting up this Brownian motion, getting rid of it. So to be left with nonlinear deterministic subsystem for which I can design, say, some type of control policy, pi star. I need some type of assumptions here. And these are standard assumptions, incremental exponential stability of the origin. And the analysis of it can be done through incremental Lyapunov functions, matrix measures, Fiedler-Lyapunov functions, and Riemannian metric conditions. Nothing new here. And now moving forward, so I have the nominal system with some policy, which was this, but now I look in the nominal system that I need for the analysis. This was the deterministic part. Now I have the true honest nominal system, and I have the true system. When I put the pi star into the true system, I augment it with some adaptive increment with the objective to keep the true distribution bounded around the nominal distribution. The bound we compute in Wasserstein metric, which we borrow from optimal transport theory. It preserves the distance and shape. It's a metric on the space of distributions. To achieve that, so as I said, we are applying the L1 adaptive controller for the augmentation, which is born in the deterministic world. But now, as I apply it, I have to acknowledge the fact that it gets the state measured by a sensor, which will be stochastic in its nature. So it brings up colored noise into the system. So it's important to understand and acknowledge now, I'm bringing this deterministic controller that gets the state measurement from a stochastic sensor. So how to deal with all of this? So it results in colored noise injection through that aleatoric uncertainty, Brownian motion that gets there. So our implementation remains in the feedback space. Our guarantees are given in the space of distributions. No need to assume unreasonable distribution of feedback. Skipping all the math now to make the Friday afternoon easy. So we get guarantees in terms of Wasserstein metric on the distributions, and we get pathwise guarantees. So we get guarantees that they are upper bounded by some terms which remain uniformly bounded away from zero. Remember, the pilot was saying there is something left there, and during the engine shutdown they had 3 degrees left, because now we get bounds that remain bounded away from zero. And one of the reasons is this independence of the Brownian motions that I emphasized. If I give up on this assumption, and in the absence of uncertainties, I'll make sure these bounds can go to zero asymptotically. But because of the independence of the Brownian motion and the presence of unmatched uncertainties, these bounds remain bounded away from zero. The Wasserstein metric will collapse to 2-dimensional Euclidean norm and recover the original performance bounds of L1 adaptive controller that we had for nonlinear deterministic systems if I take out all the stochasticities and go back to deterministic. So when I look into my pathwise bounds, there are nice terms here to observe. So we get this polylog bound, which otherwise in distributionally robust control literature, they don't have the log term. In general, the bound comes across like this. Yongxin Chen has this polylog bound from Georgia Tech, but in case he's not looking into uncertain stochastic systems, in case it's known, so we borrow lots of his analysis to get this polylog bound. Why did we care for this bound? This is the violation, the safety violation probability. This is important because this polylog bound gives you the blue curve. This bound without the polylog will give you the red curve. The planner that wants to use the bound coming from the controller would love the blue bound to get tighter performance, not the red bound. That's why this proof took us 4 years. It's a 141-page paper on arXiv, but we went through all of this. So this is like the L1 performance, like we show how the distributions match. So green is with L1, yellow is the nominal. If you see the nominal is a good Gaussian, green is not a Gaussian, but L1 makes it Gaussian, and they come and match. This is the magic of Wasserstein with the muscle of L1, like we call it. And here are the two things coming and getting one over another, but with the bound remaining bounded away from zero. If you see this bound never collapses to zero, it came to 0.7 and stood. That's the independence of the Brownian motions that was important to incorporate into the analysis. Getting back to this autonomy pipeline where we started, so revisiting the questions, what should the components communicate and what should be the language for the communication? So we use now this distributional Wasserstein bounds for setting up the optimal stochastic optimization for the planner. How we do it? So the language is the space of distributions bound in the space of distributions. So the first planner we did is this covariance steering. I presented it in CDC. So the stochastic optimization that's used for producing a motion planner is typically formulated like this, which cannot be applied to uncertain system. To apply to an uncertain system, there is this distributionally robust stochastic planner that maximizes against an ambiguity set of distributions, which hedges against the effects of worse distributions. So what we do, we take this bound from L1 and pass it to the stochastic planner. Now, so what we do, the planner requires this A set, and the A set will come from the L1 adaptive controller to maximize it. So what are the key assumptions here that we were able to read? Ambiguity sets can be determined under some scenarios. In the literature, people assume availability of sufficient samples from true distributions, which is in some sense idealistic. In some sense it may be true, but it's non-verifiable, right? So we use only feedback, one single sample at the point of the measurement. As I said, it's a deterministic controller. The literature assumes known bounds for the moments of xt. We only assume finiteness of the second moment by well-posedness. And we do not need to assume that the state distribution is compactly supported. It can be unbounded. So there are some fundamental assumptions that we have relaxed. And with that, we do this stochastic distributional robust stochastic optimal planner problem. We solve it. We get guaranteed margins on state distributions that enable high probability constraint satisfaction. And by applying this L1, here are the plots on the second slide we will show. We have safe navigation of a four-dimensional system perturbed by unknown nonlinear drift and diffusion. Without L1, when it goes through this narrow passage, it collides with the obstacles in the presence of uncertainties that you see with the blue. Here it goes through this wide opening. When it goes through the wide opening, because L1 helps to find this bound. And this is still pretty conservative. If we still add on the top of it some machine learning, maybe it can go also here safely. But still so far, there is no machine learning added. All we have done, we have matured L1 to be machine learning ready. Although we showed on imitation learning how to augment an imitation learning policy with it. But from the planner perspective, we're just getting there to be machine learning ready. Now some of the future work, where does it go? So it's a decoupled framework, as I said. We want safety to be guaranteed through the architecture, learning to be done offline, and update the bounds whenever the threshold which we specify is available. So safety is guaranteed persistently, performance is improving intermittently. So that's how we view it. Autonomous systems can be done and designed in different ways, as we know. But this is the way we go. The reason we go this way is because when we take out all the uncertainty, we are back to the deterministic bounds, gain and phase margins. If the nonlinearity goes away, it talks the Bible, current Bible of FAA in terms of certification. Now we have enabled these two frameworks talk the same language. We had a model risk certificate from machine learning, and we have now certificates of robustness over the set of probability measures for planning and control, and they can talk the same language. So we can pass the bounds to each other and enable certification of autonomous systems by raising abstractions of robustness to a higher level. With that, since we still have 20 minutes more time, I want to show some robotics applications without going through theory. Today, no matter what you do, if you don't do robotics, you can't be cool. Everything else doesn't matter. So here's an experiment that we're waiting for ICRA submission before it can go on YouTube. it locks now to grab it to go to the other side. The same white gripper, it has some softness to it, has done other experiments. So let's run this experiment. So it grabs different objects and drops them into these bins. Only here, out of these 20 steel marbles, one will fall out. Then this is perching experiment. As you see, there are different perching poles. One is a sphere, one is a rectangle, one is round, one is a little bit like trapezoidal. So it perches on all of them. So quadrotors are not robust to rotor failures, as you know. Here we have a rotor failure experiment. When one rotor fails, it's a multiple model L1 adaptive control. So we have few different models. It picks the best one. There is a fast system identification method. This paper is published in RAL. It can be downloaded. I mean, this movie is available also. So for rotor failure, it's a quadrotor, so it picks up quickly the right controller and implements it. And you see the fan blowing the disturbance, so that's why. And here is like a propeller which is glued, and it will be unglued at an unknown time. We're just showing that. So it's unglued. Now it's slow speed. Now it will go to double speed to compensate. So these are like further applications of L1. This is a soft propeller. We did it in collaboration with Japanese. You see, it's a collision compliant propeller that didn't fall from heating. This is our Omnidrone platform, which we did in collaboration with ETH from Zurich. As you see with L1, we are able to stabilize around the red point. Now you will see. So it goes around. So, but here is where we will see with L1, it remains around. Here it goes around, here it stands at the point, because there is modeling of internal rotor dynamics also here done. And here is where he flies with hand tracking. Here it will clean the emoji on this last video. If you see, here he tracks the badminton hand tracking. And on the last one, it will clean the emoji on the whiteboard. Oh, okay, it goes. So it applies force, basically. There's a cleaning device, dedicated sponge at it. So it cleans the emoji. These are things students like to play with. And something else is coming, so if it's clean the whiteboard, we can go ahead and this is landing on a moving platform where the moving platform area is very small. It again lands on it. So here it lands. So there is this reinforcement learning augmented with L1, lots of other things. This is multi-vehicle platform. Like there is path planning, collision avoidance, coordination in time. Skipping all these details, just showing 1 minute of this movie, and I will wrap up the presentation. So Okay, we'll come to that now. The coordination is achieved. So with this, I'm ready to kind of wrap up. So what we got up to now with this distributional robust adaptive control framework, we got really global results. And to bring it really to the robotics world to show the real benefits, we still have to do proofs to get the local high probability results. There's lots of work to be done here. Maybe another 10 PhD students will work on this topic to make the framework complete. We can enable fast and safe planning and reachability analysis among certain stochastic systems, enabled by these bounds and tight high probability tracking guarantees. We can couple it with state-of-the-art high probability planners for nominal nonlinear stochastic systems, get tight guarantees with numerical tractability of deterministic systems, and we can do further investigation into sampling-based stochastic optimal control algorithms. We can enable this framework to sample data systems, hybrid systems, like we showed that imitation learning, and we can do other types of machine learning algorithms as well. So what is the ethos of research, right? The ethos is that we develop it in a way so that when you take out all the stochasticity, all the uncertainties, you're back to deterministic nonlinear system. You recover the performance bounds and time delay margins of L1 adaptive control. When the nonlinearity goes away, it collapses back to gain and phase margin that can enable talking with industry easier, with FAA easier. Because people who do the machine learning, when you talk to that community, they say, oh, these are new types of systems for which FAA needs to come up with new perspectives for certification. We do domain randomization for robustification. We do all these other tricks to improve the learning algorithms, reinforcement learning, and so on. It never gets back to these known gain and phase margins. They say this is new type of systems, new Bible is needed for certification. In our case, we tried to stay on this track despite the challenges, because on the way, as 4 years we were working on this paper, there were lots of instances when, okay, you can say, I can take this assumption, give up on this, get this easier proof, quickly get the paper out. But no, we stayed on track, didn't publish till it was complete. And the challenge and desire was to enable the certification in a way that it's consistent with the existing practices as minimum. Of course, we understand one day there may be no need for all of this because things can change, technology changes, other methods are coming forward. These are some QR codes. You can capture a snapshot if you want to download the code, the papers, the software. This is the group, so I have to give credit maybe to Chengyu Cao, with whom we started the development of L1 adaptive controller. We have the book that I'm using to teach my graduate course, already 18 years at Illinois. And Aditya Gahlavad is the research scientist who stayed with me already 8 years. He did this distributionally robust L1 adaptive controller, proved all these bounds for distributional robustness guarantees. He was joined by other postdocs like Sandeep Banik, a stellar guy. So we had lots of stellar people working on this. I can't name all of them. And I want to thank all the sponsors for believing, for funding this work. This work was exceptionally well funded. I have no complaints. I'm thankful to all the sponsors, Air Force Office of Scientific Research, NASA, NSF, Army Research Office, ONR, companies that expressed interest in transition efforts, in commercialization, but above all and everyone, the test pilot school at Edwards Air Force Base that said, here is the vehicle, come and put your controller on it, fly. And the students said, okay, we'll design and fly. You know, very few people will take the risk to put their controller on a plane and fly. My students were fighting with each other who would go for the next deployment. And I'm thankful to all of them. Thank you to all of you for coming to this seminar Friday late afternoon. And with that, I'm happy to take your questions.
So yeah, thanks for the talk. So we see that L1 adaptation could handle the disturbance from the environment. How does it translate to the saying the color noise from the sensor? I think you mentioned that a bit. Do we have theoretical guarantees on that? Yeah.
Go to archive, go to the paper, right? The theoretical guarantees are there. The paper is not published. It's 141 pages. We have to come up with a way to reduce it to make it publishable.
Yeah.
We're sitting on it. We put it on archive. I say this archive simplified our life. Now we're kind of not fighting to publish. We just put papers there and cite it. And if somebody finds a mistake, let us know. But it took us 4 or 5 years really to clean that, how to do it the right way, right? And on that way, there were lots of instances, like you get attracted, oh, I can quickly do this, get this paper quickly there, no paper. So Aditya was committed. I took the risks, okay? The research scientist, the postdoc who stayed with me 8 years, he was committed. I was taking the risks. Okay, I'll get the funding, you keep working, but don't deviate the path. It takes lots of effort and coordination and collaboration to make these things happen.
Nice. Yeah. Do we have some intuition behind it before we read the 100 pages?
There's lots of math involved that we had to learn and pick up martingales, this and that, and so then this Wasserstein bounds, lots of deep detail. So the paper itself is 38 pages, but the appendices are going over 100 pages, and that's where there are lots of technicalities that most likely over the next few years one can develop. We can write it shortly because lots of the things are first time derived. But what we aim to achieve was this polylog bound that can be useful for the planner. And not that the planner people do their optimization, control people do theirs, and then all is tested in simulations. No, we can connect these bounds. If today's seminar must leave one message with you, that's it, that these bounds can be connected, the whole autonomy pipeline can be testified. But in that process, we have to be very honest with the terms, right?
Yeah.
So it's just too much now to open that math and go over it. But you go to archive, you'll find the paper. You send us questions.
Yeah. Thank you.
We can go through detailed Zoom meeting to go through details.
A question about the broken propeller, the video you're showing, drone with a broken propeller, and is the whole framework saying that the broken propeller and the good propeller, like a drone, are behaving within the similar distribution, or like there's some like system identification going on that identify the new dynamics and adapt it to
Right. There is system identification. That paper is published in RAL. You can open it. There is a fast system identification algorithm, which is what the student did. For that, he got the paper. And there are 4 models between which it's multiple model approach, really. Are you familiar with multiple model approaches that have multiple models and there is a system ID running, identifying which model is the closest to the real world based on the failure, picks up the controller from there to quickly stabilize. The point is how quickly it can identify before it crashes and how quickly it can plug in the right controller before it crashes to manage to stabilize. That was the challenge with that paper being solved. There is a fast system identification algorithm there.
So you're saying there are already a library of
library, but that library has only 5 models there.
So it's
1 is the healthy and 4 are the faulty models. Not like a library of 100 or 1,000.
Thank you.
Although in one of your papers, L1 quad, you just have an L1 adaptive control. It's able to handle a broken propeller without having the multimodal approach.
It's not a propeller. In this paper that he's saying, it's a rotor phaser.
It's a rotor.
It's a rotor
Yes,
phaser.
yes.
It's not a propeller.
I see.
Did you say propeller? No, it wasn't. No, the broken propeller in the other case that goes away, it has also the rotor failure with it. It's a rotor failure example.
Let me ask a question. I will go back more on the theory part. I'm curious, when you have this distributional robust controller, right? I mean, if I understood correctly, there is an underlying assumption of Brownian motion for the disturbance. Do I need this type of Gaussianity, let's say, for the results to scale or to prove the polylog bounds, or it can be any sub-Gaussian disturbance or anything else. So do you need a structure on?
No,
Your
no
disturbance?
structure. It's any Gauss.
Okay. Okay. Yeah. Thank you.
More questions?
Thank you for your talk. Very nice. And I think that you apply this airborne adaptive to say leg robot and so leg robot. As I think is
Like robot?
yes, I think it's in a simulation. So I assume that might be a hybrid system. I assume. So how will that apply to the Lipschitz continuous?
Right. We didn't apply it. So the group at USC, University of Southern California, applied. And we are not even co-author on that paper.
Oh.
Whether they modeled it as hybrid, I don't know. I have those movies actually in this presentation, but I didn't run it. But it's the University of Southern California that applied. Whether they modeled it as hybrid or not, to be honest, I didn't check that.
Oh, I see.
I have the nice video in case people ask. I can show the nice video. I didn't stop on that. Kept it aerospace-ish. Presentation.
Follow-up question for me, again on the distribution of robust. Can you comment on computational complexity or scalability of the methods?
No, scalability is something very important that we care very much.
Yeah.
Now you're getting into what Dennis Bernstein likes to say, kitchen sink details. Let me give you the kitchen sink details. So one of the reasons, for example, this L1 distributional robust adaptive control paper we put up on arXiv last year, April.
Yeah.
The software we only put up just 2 weeks ago because it was not scaling well. And the codes have to be written in Julia and parallelization, all these things. We take deep care for the quality of our work and also its presentation before we release it on GitHub. Now it's on GitHub, it's fully scalable. All these issues are solved. Because it's one thing you do this simple simulation that I can put in my presentation, come and do seminars, go to Air Force, NASA. It's another thing, does it in reality work like this?
Yeah,
We want it to work like this, right? And certain things are just a matter of fixing the code and the bounds. Now it's all released on GitHub. You can download and make use of it.
Pretty cool.
These are very good questions to ask.
Yeah.
You show evidence of doing experiments,
Yeah.
asking the question, right? So then I get nervous. Why isn't it pushed to GitHub? They explain me, no, somebody downloads, it's not scalable. It will not match your presentation.
Yeah.
So that's why certain things are released very late. Right?
Yeah, that's amazing. Other questions, folks? Yeah.
No other question.
Let's see if there is any on the
Zoom?
Zoom. I don't see anything yet. So let's thank the speaker. Thank you for the amazing talk. Great.